Good afternoon, everyone. I welcome you all to this next lecture of Dynamics of Machine. And in today's lecture, we are going to discuss about the partial balancing of the locomotives. All right. Uh, in the previous lecture, we saw about the balancing of the reciprocating parts. So, how to do the balancing, that is partial balancing can be done, complete balancing cannot be done. And while doing that partial balancing, we uh, came across two forces, two unbalanced forces. One was across the one was along the line of stroke, and second one was the perpendicular to the line of stroke. Okay, so this is what we discussed in the last lecture, and we also saw the expression. We derived the expression by which we can determine the unbalanced total unbalanced amount of unbalanced force present in the present due to reciprocating parts. All right, now this is in continuation to that only, that partial balancing of locomotive. Now locomotive, as you might have seen, the old engines, steam engine, right, in which if you have seen the side view, or in today's train engines also, if this is a wheel and this is another wheel, so one internally they will be connected like this, and also there is another link which is connected like this. Okay, so when this rotates, this another link also rotates. This will go like this and this. Okay, so these the things which have been developed, these balancing and all, these were primarily developed for this steam engine only. Okay, to run the steam engine, which was developed by Dr. James Watt. All right. So all these terms which we are studying, that is governor and this balancing slider crank mechanism, this dynamics of slider crank mechanism, this all is generated from the application of steam engine only. All right. So therefore, this also we are going to study in that terms. So the locomotive usually has two engines. So that steam engine used to have two slider cranks mechanism placed side by side to each other. All right, and both their positions were at right angle. For example, if the crank of first locomotive, if the crank of first slider crank mechanism is at 0 degree, then the crank of the second slider crank mechanism would be at 90 degree from this. Okay, so one question may arise that why we did not keep at 180 degree to each other. Okay, so it was also done initially. So if one position is like this, the crank of the second, let's say we are viewing this view. So this is one wheel and this is another wheel. Okay, and the engines are kept like this. Okay, so this is the line of stroke, let's say, and one of the crank is at some angle theta. All right, then the other crank, the crank of the second slider crank mechanism, would be at this angle, and this angle would be 90 plus theta. Okay, so this will be the this is something arrangement of two slider crank mechanisms in a locomotive. Now one can ask a question that why we haven't kept mm, the second crank at this angle, that is theta plus 180 degree, opposite to this, right? It would have been very convenient, and uh, it would have been balanced many things, right? But it is not done in such a way. Why? Because this position is called the toggle position. Okay, one crank is like this and another crank is like this, and angle between them is 180 degree. Okay, this is not kept like this because this is the toggle position. Okay, and once the vehicle gets locked in that toggle position, then it is very difficult for it to remove from that position, right? So to avoid being stuck in the toggle position, because then the cranking of the engine by giving so much of force to the piston would have been very difficult. Okay, because this position needs so much amount of force for doing the cranking. That is the starting of the engine. All right. Therefore, they are not kept at 180 degree to each other. All right. So I hope it might be making some sense to you, or you might have understood why they are not kept at 180 degree from each other. Uh, all right. So the two-cylinder locomotive may be classified as the inside cylinder locomotive and the outside cylinder locomotive. So the inside cylinder locomotive can be seen in this diagram. These are the driving wheels outside, these are the wheels, and inside there are two slider crank mechanisms. So over here and over here, okay, and crank positions are 90 degree to each other. All right. Similarly, for outside cylinder locomotives, the wheels are inside and the mechanism is placed outside the wheels. Okay, and again cranks will be at 180 at 90 degree to each other. All right. Now, the locomotive may be further classified into single or uncoupled locomotive or a coupled locomotive. Now, what is meant by this? A single or uncoupled locomotive is the one in which the effort is transmitted to one pair of the wheels only. That is, all the force produced by this slider crank mechanism will be transmitted to only one pair of wheels. Whereas in coupled locomotive, the driving wheel are connected to the leading and trailing wheels by an outside coupling rod. So a coupling rod is attached to the wheels in order to give the driving force to both the wheels. Okay, that is leading and trailing wheels both. So I hope this is clear to you, and this diagram is also clear to you how the arrangement is done. So this is the oblique view. This might be the front view or the side view. This is the oblique view. Okay, fine. Let's move forward. Now we'll be going through the effect of partial balancing of locomotive. Okay, what are the effects which came into the picture because of partial balancing of these locomotives? Right. So, in summary, I would tell you that uh, while studying the slider crank mechanism, that is partial balancing of reciprocating parts of the slider crank mechanism, we came to the conclusion that there will be some amount of unbalanced force which will be along the line of stroke, and some amount of unbalanced force uh, will be coming perpendicular to the line of stroke. Okay, so the horizontal unbalanced force, the component of unbalanced force which is in horizontal direction, will be having two effects. That is, first effect will be variation in tractive force, and second effect would be it will be producing a swaying couple. Okay, so these are the effects of the horizontal unbalanced force, and the vertical component of the unbalanced force would be producing a hammer blow. Now, what is meant by all these three things, we will be studying in the further slides in this lecture. Okay, so let's just quickly read this. So as we discussed that in the reciprocating parts, only partially balanced, right? Due to the partial balancing the reciprocating parts, there is an unbalanced primary force along the line of stroke, and also an unbalanced primary force perpendicular to the line of stroke, that is horizontal and vertical. The effect of unbalanced primary force along the line of stroke is to produce. So along the line of stroke, it will have two effects, that is variation in tractive force, and there will be a swaying couple. Okay. Now, effect of unbalanced primary force perpendicular to the line of stroke will produce pressure on the rails, which will result in hammering action of the rails. So, because that is vertical in direction, so it will try to lift the wheels of the steam engine, and once that its direction changes, the wheels will strike on the rails uh, by so much amount of pressure. So it is why we kept the name as hammer blow, because you might have heard any while uh, doing some practices in the workshop, that when you are hitting the hammer on the anvil, right, so the kind of noise which is produced during that, the same kind of noise was produced when the wheels were striking the rails. Okay, so that's why it is named as hammer blow. Now, as I told you, that due to horizontal unbalanced force, there is variation in tractive force and a swaying couple, and because of vertical unbalanced force, there is hammer blow. Okay, so these three things we'll be studying today in this lecture. All right, so let's move forward. Let's first see the variation in the tractive force. Okay, now see, variation in the tractive force is because of uh, unbalanced force in the horizontal direction, right? So what was the amount of unbalanced force? That is 1 minus c m omega square r cos theta, right? This is what we saw in the previous lecture. Okay, so in the previous lecture, we saw how this component, how this expression was derived. All right. Now, uh, so since there are two slider crank mechanisms, and both the cranks are placed at an angle of 90-degree apart from each other. So if one crank is having this much amount of unbalanced force, the other crank will be having this much amount of unbalanced force. The only difference will be the angle would be cos 90 plus theta. Okay, so in order to determine the total track variation in tractive force, what we'll do is we will add both these unbalanced forces. Okay, so this is what is done over here. Uh, the unbalanced force along the line of stroke of cylinder 1 is 1 by 1 minus c into m omega square r cos theta, and unbalanced force of cylinder 2 would be 1 minus c m omega square r cos 90 plus theta. Okay, now, as per the definition of the tractive force, it is the resultant unbalanced force along the line of stroke. So, total unbalanced force along this line of stroke of this piston is called as tractive force. So, what we are going to do is we will add the total tractive force produced by both the uh, slider crank mechanisms, and that will be 1 minus c m omega square r cos theta plus 1 minus c m omega square r cos 90 plus theta. Now, you already know that cos 90 plus theta is equals to minus sin theta. So, this total tractive force, that is Ft, comes out to be 1 minus c m omega square r cos theta minus sin theta. All right. So, this is the amount of tractive force which will be produced at any angle theta. Okay, you will put the value of theta, and at that position of the crank, you will get the total tractive force. But what we want to do is we want to find out the maximum amount of tractive force. So for finding this maximum amount of tractive force, what we will do, we'll differentiate this equation in terms of theta and will equate it to 0. All right. So as you might have studied in the maximum minimum in the mathematics, this is what we do. So that maximum and minimum tractive force, when it will occur, when this uh, term, because while differentiating with theta, rest all terms will become constant. Only these are the variables, and these are to be differentiated with respect to theta and equated to 0. All right. So the angle which came out to be, that is 135-degree and 315-degree. Okay. So the total tractive force for maximum and minimum amount is will be at angle 135-degree and 315-degree, and tan 135-degree and 315-degree, its value is under root 2. Okay. Mm, so at 135-degree, its value is under root 2, and 315-degree also, its value is root 2. But only difference comes in the plus and minus sign. So therefore, maximum and minimum tractive force would be plus minus under root 2, 1 minus c m omega square r. Okay. So I hope this is clear to you, how the variation in tractive force is there, because there is unbalanced force along the line of stroke. Okay. Now let's move forward. So the second effect of the unbalanced force in horizontal direction was the unbalanced force will produce a swaying couple, right? So this swaying couple is acting along this line of stroke. Okay, so let's assume a value that both the line of strokes are at a distance of a from each other, as shown in this figure. All right, and this A can be equally divided into A by 2 and A by 2, okay, from a common point, that is this y axis. So what this will do, that these are unbalanced forces, and we will take its moment about this axis y. Okay, so this downward force, that is r cos 90 plus theta, this will try to do this moment, okay, and this above force, that is 1 minus c m omega square r cos theta, it will try to turn it in this way. All right. So there will be a couple which will be in opposite direction to each other. Now this couple has swaying effect about the vertical axis. So about this vertical axis, this will be, and this engine will try to sway from its uh, line of motion. All right. So one will be in clockwise and another will be in anti-clockwise direction. Hence, this couple is known as swaying couple. All right. And as I told you, this A is the distance between the center lines of the two cylinder. So the swaying couple would be this force, that is 1 minus c m omega square r into A by 2. Why A by 2? Because distance from this axis is A by 2. Okay. This force is at a distance of a by 2 from this axis. All right. And since it is creating anti-clockwise moment, therefore it is taken with positive sign. Now the second force, because of the second line of stroke, would be 1 minus c m omega square r cos 90 plus theta multiplied by this distance a by 2. So force multiplied by distance will be couple, and since it is producing clockwise couple, therefore it is taken with the negative sign. All right. So again, this entire thing will come common, and as you know, cos 90 plus theta is equals to minus sin theta. That minus sign is taken inside, so it will become positive. Okay, so cos 9 theta plus sin theta. So this is the total amount of value of the swaying couple. Okay, this much amount of swaying couple will be produced. So at any given value of theta, we can calculate the amount of swaying couple. Now again, what we want to do is we want to find out the maximum and minimum value of this swaying couple. So again, we will differentiate this cos theta plus sin theta with respect to theta, and we'll equate it to 0. So what we'll find out, that value of theta when it is 45, its value is maximum, and when the theta is 225 degree, its value is minimum. Okay, and its magnitude is plus minus a by root 2 1 minus c m omega square r. So if in the question it is asked that find the maximum or minimum value of the swaying couple, we are going to use this expression. Okay, so let me just draw it over here. This expression we are going to use. Now, what this note is saying is, as this value of C, in the last class I told you that this value of C varies from 20% to 60-70%. Okay, so but in order to reduce this swaying couple, because nowadays there are more than two engines are used, maybe four engines or six engines or eight engines. Engine, by engine I mean the slider crank mechanism in a single engine. Okay, like two slider crank mechanisms are used over here, but nowadays more than two slider crank mechanisms can be employed at a single time. Okay, so in that case what happens, there will be a large amount of force, and hence this swaying couple will be very high. Therefore the value of this c is taken as maybe 40% or 30% from the total m into r value. Okay, so this is what it is saying. All right. Now we have discussed two things, that is effects of horizontal unbalanced force. So we discussed variation in tractive force and variation in swaying couple. Now the third thing is effect of this vertical unbalanced force, and that effect is known as hammer blow. So let's just discuss that. All right. So hammer blow is because of the vertical component of the unbalanced force. Okay, and it will be perpendicular to the line of spoke. So it will try to uh, bring the rails. It will try to push the wheels above from the rails. All right. So now this uh, its value. What was the value of unbalanced force? It was b omega square b sine theta. So the vertical component of the unbalanced force was b omega square b into sine theta. But what will be its maximum value? Its maximum value will be when sine theta is equals to 1. So sine theta is 1 at 90 degree and 270 degree. So the maximum value of hammer blow would be b omega square multiplied by b. All right. Now this will be balanced. This we will try to balance it by the wheels, and that is the mass of the wheels and the other parts which are attached on the engine. Okay, but this hammer blow is its effect is so high that the value that the even having a large amount of mass over it, it will try to lift. All right. So we have to see when its value is exceeding this weight of the wheel. So let P be the downward pressure on the rails or the static wheel load. Okay. So P is nothing but the weight of the wheel or the downward pressure it is exerting on the rails. Okay. So what will be the net pressure? Net pressure of the wheels would be P plus minus B omega square B. Why? Because this is the balancing of the rotating mass, and the rotating mass keeps changing its direction all the time. Okay, so when the direction of this is downwards, then nothing will happen. But when the direction is in the upward direction, its value will exceed the value of the weight of the pressure, that is of this value of this pressure. Okay, so when its value exceeds more than the pressure, then it will try to lift the wheels of the rail. Okay, and when those wheels come back and hit the rail, that is called as hammer blow. Okay, so if P minus B omega square is negative, then the wheel will be lifted from the rails. Therefore, the limiting condition in order that the wheels do not lift from the rails is given by P is equals to B omega square B. So the maximum value which we can allowed for this B omega square B is equals to the weight of the wheel. Okay, and by this there uh, came out to be a permissible value of the angular speed. That is, we cannot increase the speed uh, of the rails more than this. That is, omega is equals to under root of P upon B into B. It is done from this equation only. Okay, so whatever the value of this comes out to be, we cannot increase the angular speed of the slider crank mechanism or the wheels from this. That's why in the previous times, the speed of the locomotives were restricted to very less amount as compared to today. That is 60 to 65 kilometers per hour. Okay, because if the engine runs at more than that speed, this hammer blow condition was occurring. All right. Therefore, this was the speed was limited to 60 to 65 kilometers per hour. Even in today's normal these trains in India, the maximum speed it goes is up to 90 or 80 kilometers per hour. Okay, but there are other trains also, such as Shatabdi and Duronto, etc., and these uh, other new railway projects which are going on. In this, they have increased the speed up to 135 or 150 kilometers per hour. Okay, so this what we are studying is of initially development of the steam engine. Okay, therefore its speed was limited by this value. All right. So these were the practical problems which were faced by Dr. James Watt while running his steam engine. Okay. So these are the solutions which he came out with, and by determining the maximum and minimum value, we can find out the limitation in which we have to run the rail. Okay. So I hope this is clear to you. All these three all these three effects of the partial balancing of reciprocating masses. Okay, that is variation in tractive force, swaying couple, and the hammer blow. Okay, so hope this is clear to you. Thank you for joining. Have a good day.